Welcome back, everyone. I'm your AI quantum architect. Today, we're going to take what we learned previously and apply it to a new scenario. We're going to use Shor's algorithm to mathematically dismantle the protection on a very common password, pass W0123. We will see how this text becomes a number, how RSA hides it, and how a quantum computer using the power of period finding exposes the secret keys. The digital transformation of pass W0123. Welcome back! To understand how Shor's algorithm destroys encryption, we first have to understand what it's actually attacking. Computers are brilliant at math, but they're illiterate when it comes to text. They don't see the letters P at SSW0RD. To an RSA system, your password is just one incredibly large, unique number. Let's look at the three-step digestive process that turns your text into math. Layer 1, the ASCII translation. First, we have the ASCII conversion. Think of ASCII as the universal Rosetta Stone for computers. Every character on your keyboard, whether it's a capital letter, a symbol, or a digit, has a specific numeric code assigned to it. For our password, the capital P is recognized as the number 80. That @ symbol becomes 64. Even the numbers in your password aren't treated as values yet. The digit 1 is simply code 49. At the end of this step, our password has become a sequence of 10 distinct integers. Layer 2, packing into hexadecimal, or base 16. This is the native language of computer memory. It's more efficient than our standard decimal system. Our P, which was 80, is written in hex as 50. The @ symbol becomes 40. If you looked at your computer's raw memory while you typed this password, you would see a string of hex bytes like 50, 40, 73, 73, 70, 72, 64, 31, 32, 33. We have moved away from human language and deep into the machine's architecture. Layer 3, the birth of the big integer. Finally, we reach the most critical step, integer concatenation. RSA doesn't encrypt these characters one by one, it encrypts them all at once as a single block. The computer takes that long string of hex values and treats it as one massive, continuous number. Mathematically, we call this value M for message. For pass W0123, M becomes this incredible number. This 23-digit giant is what actually enters the RSA pipeline. It is this number that will be raised to a power and hidden behind the complexity of modular arithmetic. Now you know the truth. Your password is a mathematical target. When we talk about breaking encryption, we aren't guessing letters, we're performing surgery on this specific integer, M. In our next segment, we'll see how RSA tries to hide this number and why Shor's algorithm is the ultimate master key.
The mathematical shield, RSA encryption. We have our password, and we've converted it into a massive integer. But right now, it's still naked. If an attacker saw that number, they'd have your password instantly. To hide it, we use the RSA public key. In our example, we're using an exponent of 5 and a modulus of 91. Think of these as the public instructions for locking a digital vault. Step 1. RSA math happens within the neighborhood of our modulus, 91. Before we encrypt that 23-digit giant we created in the last step, the system performs a quick reduction. We find the remainder of our big number when divided by 91. In our case, that remainder is 65. This is a mathematically sound shortcut. In modular arithmetic, the big number and its remainder behave identically. So, for the rest of this process, we're working with the number 65. Step 2. Now we apply the core RSA formula. We take our message, 65, and raise it to the 5th power. Now, 65 to the 5th power is over 1 billion. It's a huge number. But remember, we are in clock math world. We don't want the billion, we want the remainder after dividing that billion by 91. To do this efficiently, computers use a trick called repeated squaring. Instead of one massive calculation, they break it down into smaller, manageable squares and products. It's like climbing a ladder instead of trying to jump to the roof in one go. Step 3. After running the modular exponentiation, we get our result, 39. This is the ciphertext. Think about what just happened. We started with a complex password, turned it into a massive integer, and through the meat grinder of modular math, it came out as the number 39. To anyone watching The Wire, the number 39 is meaningless. It doesn't look like password 123, and there is no obvious way to turn a 39 back into a 65 unless you have the secret key. This is the classical wall of security. To reverse this math, an attacker has to factor the number 91 back into its primes, 7 and 13. With small numbers, it's easy, but with the massive numbers used in the real world, it would take a classical supercomputer trillions of years. That is, until we introduce a quantum computer. In our next segment, we'll see how Shor's algorithm walks right through this wall like it isn't even there.
Shor's algorithm, the secret door. Remember that classical wall we talked about? The one that takes a supercomputer trillions of years to climb? Shor's algorithm doesn't bother climbing it. Instead, it finds a secret door built into the very rhythm of mathematics. While a classical computer has to guess every prime number one by one, a quantum computer uses quantum interference to see the answer all at once. The power of period finding. The heart of Shor's algorithm is a trick called period finding. It turns the problem of factoring numbers into a problem of finding a repeating pattern. Imagine a clock with 91 hours on it. If we keep multiplying a number by itself inside this clock, the results will eventually start to repeat. For our modulus, 91, a quantum computer can look at every possible power simultaneously. It doesn't check them individually. It uses quantum waves to cancel out the wrong answers and amplify the right one. Factoring 91 in a flash. In our example, the quantum computer quickly identifies that the sequence repeats every 12 steps. This 12 is the period, the magic number that breaks RSA. Once we have this period, the hard part is over. We just use a bit of simple classical math called the greatest common divisor. We take half the period, which is 6, and look at the numbers around it. Specifically, we look at 2 to the 6th minus 1, which is 63, and 2 to the 6th plus 1, which is 65. When we compare these to our original modulus of 91, the primes are exposed instantly. 63 and 91 share a factor of 7. 65 and 91 share a factor of 13. The foundation collapses. The wall hasn't just been climbed, it has been demolished. By finding 7 and 13, the quantum computer has factored n. With these two primes, we can now calculate the secret totient, find the private key D, and decrypt our ciphertext 39 back into the original message 65. The quantum reality. What took us seconds with the number 91 will take a fault-tolerant quantum computer only a few hours with a 2048-bit key. The unbreakable security of the modern world is suddenly transparent. In our final segment, we'll discuss what this means for your data today and how we're racing to build new walls that even a quantum computer can't jump. We've reached the end game. Shor's algorithm has performed the impossible task. It found the primes 7 and 13. To a classical computer, this was a lock with no key. But for our quantum-enabled attacker, the vault door is now swinging wide open. Let's watch how the rest of the RSA architecture collapses in 3 final steps. Step 1. The secret totient. First, we calculate the totient, written as phi of n. This is the secret mathematical framework that RSA uses to link the public and private keys. Since we now know our primes are 7 and 13, the calculation is simple. We subtract 1 from each and multiply them together. 6 times 12 gives us 72. Think of 72 as the hidden rhythm of our encryption. Without the factors 7 and 13, this number is invisible. With them, it's the first piece of the master key. Step 2. Forging the private key. Now we find the private key, D. We need a number that when multiplied by our public exponent, which was 5, leaves a remainder of 1 when divided by our secret totient, 72. After a quick calculation, we find that D equals 29. Why? Because 29 times 5 is 145, and 145 divided by 72 leaves a remainder of exactly 1. We now hold the private key that was supposed to be kept secret by the password owner. Step 3. The final decryption. Now for the moment of truth. We take our meaningless ciphertext, the number 39, and raise it to the power of our stolen private key, 29, all within our original modulus of 91. M equals 39 to the 29 modulo 91. As the math resolves, the result drops out perfectly, 65. That 65 is the exact same message integer we started with before the encryption process began. The final reveal. All that's left is to reverse the digital transformation we saw at the beginning. We take the integer 65, convert it back into hexadecimal, map those bytes back to the ASCII table, and there it is. PASSWRD123. The encryption didn't fail because the formula was broken. It failed because the classical wall of factoring was obliterated by quantum power. The quantum horizon. Why we must act now. The global impact. We've just watched a password get torn apart using nothing but modular arithmetic and a quantum shortcut. But the reality is much bigger than a single password. Every time you buy something online, every time a bank transfers funds, and every secret held by a government is currently protected by the very same math we just broke. The security of the digital world is built on the assumption that factoring large numbers is hard. Shor's algorithm proves that for a quantum computer, it's actually quite easy. Harvest now, decrypt later. This leads us to a terrifying strategy known as harvest now, decrypt later. High-level adversaries are already capturing and storing massive amounts of encrypted data today. They can't read it yet, but they are waiting. They are betting on the fact that within a decade, a large-scale quantum computer will exist, and all of today's secrets, from medical records to national security intelligence, will suddenly become transparent. This makes quantum security a problem of the present, not just the future. The race to post-quantum cryptography. But there is a solution. We are currently in the middle of the most significant cryptographic migration in human history. We are moving toward post-quantum cryptography, or PQC. These are new mathematical puzzles, often based on complex multidimensional grids called lattices, that are designed to be so messy that even a quantum computer cannot find a period or a shortcut through them. Key takeaways. As we conclude, remember these 3 points. Shor's algorithm changes the rules of the game by turning a trillion-year factoring problem into a task of mere hours. Current encryption is like a safe with a timer. We don't know exactly when the timer hits 0, but we know it's counting down. The transition to PQC is the only way to ensure our digital lives remain private in the 21st century. Thank you for joining me on this journey through the mechanics of Shor's algorithm. If you want to stay at the forefront of the quantum revolution, make sure to subscribe, follow AI Quantum Secure. I'm your AI quantum architect, and I'll see you in the next lesson as we explore the walls we are building to stop the quantum threat.